Right. So I created a hybrid out of my broken mics. All my mics are malfunctioning and or broken. So I created this amalgamation. Hopefully something is working. Let's yeah, sounds actually la li la 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 la. One lonely night. La 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 la. One lonely night. Mm-hmm. Mm-hmm. Very nice. Okay. Let's. Okay, this should be fine. Let's take this link. Where I didn't take it. And paste it here. And take this link and paste it here. And paste this. Paste this. Oh, let me share. I didn't share anything yet. Present. Let's present Discord for now. Okay. Let's shut this down. This we can shut down.
Length contraction predicted by special relativity. That topic is one of my very favorites because it demonstrates relativistic length contraction of velocities under a centimeter per second. But many of you asked for an explanation not of electromagnets but permanent ones, and that's a very interesting question. Let's dig into it.
So how do permanent magnets work?
The question of how permanent magnets work is certainly interesting. Magnets most definitely seem like magic.
Now that's a permanent magnet. How does that work?
It turns out that a lot of things have to line up just so to make a permanent magnet. The relevant phenomena involves fundamental particle physics, atomic physics, and small-scale physics, sizes in the ballpark of a fraction of a millimeter. It's all very complicated, but hopefully I can make it clear. So first, the basics. Magnets have two poles, a north and a south. You can't have one without the other. Like poles repel and opposite poles attract. And two magnets pointing in the opposite direction cancel each other out, leaving no magnet at all. Magnets are made of atoms, and therefore the origins of magnetism must come from the atoms or the constituents of atoms and how they move. The relevant bits of atoms are electrons and protons, both of which have electric charge and both of which can move. Moving charges generate magnetic fields. I made a video about that. It was a way cool video, by the way.
So he claims both of which can move, and the motion creates the magnetic field or forces. Okay.
Let's see if the moving charges of the atom play a role. Protons are about 2,000 times heavier than electrons, which means that they're harder to move. So the motion of protons is basically irrelevant. But what about electrons? Their motion is much greater. And if an electron orbited an atom like a planet orbits a star, that circular motion would make a magnet. But electrons don't move that way. Instead, they're found inside clouds surrounding the atomic nucleus. They move in all directions, and the net effect is that the motion of the electrons doesn't generate significant magnetic field. What about the protons and electrons themselves? Back in 1922, in what is now called the Stern-Gerlach experiment.
1 second. So let me check the audio. Mm-hmm. 1 second. So let me check the audio. Okay. Sounds fine. Mm-hmm. Let me check the battery. The battery's fine. Okay. Mm-hmm. Mm-hmm. Okay.
Researchers proved that each electron is a tiny magnet all by itself. A decade later, a team led by Otto Stern showed that protons are magnets too. So maybe that's what makes a magnet? It turns out that the strength of a proton magnet is about 700 times less than an electron magnet, so we can ignore the protons entirely, at least from a magnet point of view. That leaves the electron. Are electrons what cause a magnet to be a magnet? Well, yes, but it's more complicated than that. To begin with, what causes an electron to be a magnet? The short answer is nobody knows. It's like other questions. Why?
Nobody knows. Particle and wave.
Why does an electron have a wave and a particle nature? Why does it have an electric charge?
I mean, it has to be a wave because of the ether. It cannot be a particle because of the ether. The question is, why does it seem like a particle when it goes through a cloud chamber? That's a good question, but that is a good question. It should be a wave. Why does it collapse into a particle? That's a good question.
Why does it have a mass it does? Why does it act like a tiny magnet?
Well, the mass is the interaction with the Higgs mechanism. I mean, everything has to have an answer. We can't, as long as we say we don't know, then we need to keep on trying to figure things out. We can't just say we don't know and move on. We need to keep trying to figure things out.
Why do people put ketchup on hot dogs? All of those are questions with no good answers. They're just facts for which we have no good explanation. I don't know, maybe Freud figured out the whole ketchup thing. But for the rest, like the strength of the magnet for a single electron, this is just the way the universe is. Figuring out why, we'll have to wait for some future discovery.
Okay, so we need to keep working for that, we need to figure out that future discovery. We need to keep working at it. We can't just give up. And it sounds like people have given up.
So is the intrinsic magnetic strength of electrons the cause of permanent magnets? Well, yes. But why but? It's because there's more to the story. Let's move to the next chapter of the story. According to the Schrodinger equation and confirming measurements, of course, atoms have a series of recurring configurations called energy levels. Each energy level can accept a different number of electrons, 2, 6, 10, 14, etc.
2, 6, 10. What do you mean 2, 6, 10? I don't know what these energy levels are. Never heard of these energy levels.
These energy level configurations explain why the periodic table of elements is the shape it does.
I never heard of this. I've never seen anything like this.
Now, just why all of that is true will take several videos to explain, and we don't have time to do it here. For now, just accept it as true.
Except what? What? I never heard of energy levels.
There's another restriction from quantum mechanics that is relevant here, and that's how the electrons are allowed to enter each energy level. For half of the electrons in an energy level, the magnetic electrons can be oriented in one direction. But once you hit the halfway mark, the rest of the electrons have to be in
I don't know what an energy level is. So right now I'm completely baffled. I don't know what's going on.
the opposite direction. This is simply because of the laws of quantum mechanics and how particles with a spin of an electron congregate together. So let's see the consequences of that. I'll use one of the energy levels that contain 10 electrons as an example. Remember,
I don't know what a 10 electron energy level is. This is useless. What is an energy level? It would take 10 videos to make. I don't know what an energy level. I never heard of an energy. I never heard of an energy level. Could you please explain that? When was this video made? This is a year ago, less than a year ago. Okay. All right. I never heard of an energy level. Could you please explain that? I think I have nothing else to see here.
This video shows a series of simulations involving a small particle. We'll start using the assumptions of classical physics. First, we'll describe the initial setup and then play the simulation. For simplicity, we'll assume a one-dimensional space, so the particle can only...
Well, this video sounds like it should be really simple, but I have no idea what's going on here. So I don't know what to do with this video.
That show up near the end of a chemistry class. Hey, crazy. They're those weird-looking shapes that show up near the end of a chemistry class. The problem is, they're always so static. The universe isn't static, it's dynamic. It's all about change. Atomic orbitals are no exception. Let me show you the way they were meant to be seen. This episode was made possible by generous supporters on Patreon. Our first obstacle is going to be that we can't actually see any of this, at least not directly. The super tiny wavelengths of visible light are thousands of times larger than an atom. Optical images just aren't possible at that scale. The best we can do is a diagram based on electron microscope data, times larger than an atom. Optical images just aren't possible at that scale.
So what is an H? What is an S? S, H. I don't know what these are. What's an S? H? Hydrogen? What is S? What are these things? 0.0529 nanometers. 0.18 nanometers. I don't know what those are. S orbital, maybe? I don't know. When was this made? 3 years ago.
The best we can do is a diagram based on electron microscope data. Every one of these spherical lumps.
Electron microscope data. So why is an electron microscope able to see more? Anyway, oops, misspoke. Scanning tunneling microscope.
Is a gold atom. That makes atoms look like tangible little balls, which they aren't, and it doesn't tell us much about what's happening inside. I mean, with some...
It makes them look like something which they're not. I hate it when they say that. I mean, how do you know they're not? What are they really? It's always they're not this, they're not that, they're not, they're not, they're not. Everything is not. So what is it? Maybe stop saying what they're not, start saying what they are.
such a simple image. There could be cake in there.
What is an S? What are we looking at?
Atoms look like tangible little balls, which they aren't, and it doesn't tell us much about what's happening inside. I mean, with such a simple image, there could be cake in there.
What is that?
Spoiler alert, it's not cake. The cake is a lie. I think it's pretty common knowledge at this point that atoms are made of three things: protons, neutrons, and electrons. They're called subatomic particles, for obvious reasons. Based on experiment, we know the heavy protons and neutrons are packed into a tiny nucleus, and the electrons...
Okay, 1 to 10 femtometers, 10 to the negative 15. Okay.
fill a volume 100,000 times larger.
Okay, the volume, there's 100,000. Okay, the volume of the electron shell. Okay. Let's say even a million. It's a million times bigger than the nucleus. That's where the electron lives. Okay.
The complete collection is what we call an atom. Since electrons fill the vast majority of the volume of their atom, they tend to control what their atom does. This makes understanding their behavior extremely important. But figuring that out was a pretty difficult process, historically speaking. To the timeline! We went from floating in the mist, to orbits, to circuit...
Okay, so 19... Oh, so this is 1905. This is 1904. So 1904 is plum pudding model. 1911 is the solar system model. 1924 is the wave orbit model. Really?
circular standing waves, all of which were ruled out by...
That's an interesting... the standing wave is really interesting.
experiments. By 1926, we were left with only one option: quantum mechanics. Which, as many of you know, borders on absurdity. Quantum mechanics is weird, y'all. You can quote me on that. And if we're wrong about it, the universe can only be weirder than we already think it is. Remember, we ruled out all the normalcy.
I don't like it when they say the universe is weird. If something... Your job is to explain the universe. If you're unable to do it, then say, I am unable to do it. Don't say the universe is weird. The universe is not weird. I don't even know what that means. What's your scientific definition for the universe is weird?
It's weird, y'all. You can quote me on that.
No, the universe is not weird. You feel the universe is weird. So you were given one job to figure out the universe and you can't. So you have failed. That's fine. So just say so. So far, we have failed to explain this phenomenon. For many years, people have failed to explain many phenomenon, and it just takes time. And then we look back and we say, "Oh, how dumb were we that we couldn't figure out something so simple that now we understand it, and it's really very simple." So right now, quantum mechanics looks like it's insurmountable, like it's unresolvable, but that's what every problem looks like just before you resolve it. So stop complaining and get to work. But stop spreading this loser attitude. This is a loser attitude. This attitude that it's unresolvable, that if somebody comes up and says, I'm going to figure it out, you make them look like an idiot. You make them look like they're trying to be smarter than Einstein. So that's not productive. So stop being so unproductive or counterproductive. What's the point of continuously repeating this claim that it's weird? I don't know what that means. Just say we have yet to figure this phenomenon out. That's it. But we're working on it. We're making progress slowly. We're running experiments. We're getting more data. Soon we'll have maybe AI that will give us more insight. So just stop spreading this loser attitude.
And if we're wrong about it, the universe can only be weirder than we already think.
The universe cannot be weirder than anything. The universe has always looked weird before we cracked it, and then it looked simple. It ends up always being mechanical, and that's the scientific assumption. And the universe seems to be mechanical. There's no, I cannot imagine a universe that is not mechanical. What is it? If it's not mechanical, then what is it? I cannot imagine a non-mechanical universe. So I don't care. I don't know what it means weird. You haven't figured out the mechanics. That's all you're saying. That's fine. Then get to work. Stop wasting time. What's the point of repeating this attitude that we haven't figured this out? This we have not figured. Why do you keep repeating it? Why do I care? Why are you not working on the problem? Why aren't you bringing up potential answers?
I think it is. Remember, we ruled out all the normal stuff. Is this where atomic orbitals come in? Yep. Let me make something absolutely clear, though. Electron orbitals are not orbits, like at all.
Okay, they're called orbitals. They're not called orbits. That's okay.
Like any quantum state, an orbital is a state of probability. Yes, really. Here's an example.
I don't know what that means. So you cannot use words that are not mechanical. So I don't know what probability means in terms of mechanics. You can talk about the probability of some mechanical flipping of some mechanical coin. But to tell me that it is a probability, that is nonsense. That doesn't make sense in English. That's not a sentence in English. I cannot imagine that. So stop saying that. That's a lie. Stop lying. Just get to work. Give me a mechanical answer. This guy, he calls himself the Science Asylum. He has 687,000 followers on YouTube, and he keeps spreading this literal disinformation. Something that obviously cannot be true because it doesn't make any sense. That's what they keep spreading. Literal disinformation.
Are not orbits, like at all. Like any quantum state, an orbital is a state of probability.
So like any quantum state that he has not defined, I don't know what it means, like any quantum state.
Yes, really. Here's an example. Are not orbits.
That's the definition of the word really does not fit into that sentence. You cannot say really something that is ridiculous, like it's a probability, whatever. That's not real. That's not the definition of real. Real is mechanical.
Like at all. Like any quantum state, an orbital is a state of probability. Yes.
It's a state of probability. That's the most... What does that mean? What is a state of probability? You cannot have a state of probability. That doesn't mean anything.
Really. Here's an example of an orbital.
And then he says, really.
Brighter spots are where you're more likely to find an electron, and darker spots are where you're less likely to find one.
Okay. That's like flipping of a coin. So something is causing the electron to show up somewhere over here and less likely somewhere over there. Something is causing that.
But the truth is, we don't actually care that much about where electrons are. Position is a pretty point.
We don't care where electrons actually are. I mean, I don't know what it means we don't care. I mean, I'd like to know what's causing the electron to sometimes show up here and other times show up there, especially when we also know that electrons are wavelets. They go through two huge slits simultaneously. So an electron is huge. 1 second. Somebody keeps calling me. Who is that? What is going on here? 1 second. Let me text her. Trying to create a new contact. Oh, there it is. I don't know her name. I think it's probably someone from a dating site. Just gonna text her. I'm not gonna text her. Forget it. I'm not gonna text her. It's fine. Because I am right now. Oh my god. She keeps calling. Let me text her. One second. Okay, let's continue listening to Nick simultaneously. This is going to be confusing. She's going to text me. Okay, let's wait for her to text and then we'll reply. Okay.
Property. What do we actually care about then? Energy and volume. But the truth is, we don't actually care that much about where electrons are.
I don't know what that means. We don't care. I mean, I want to understand what's going on in. I want to understand what's going on. I mean, this thing, sometimes the electron is super, super tiny. Other times it's huge. It's absolutely huge. It's as big as things that we can literally see when we're not looking. We know it's got to go through two. It looks like it's going through two huge slits, macro slits, that we can see the slits. So it's big enough to go through these huge slits, but then it's also tiny that we can't even see it with a microscope. So I'm confused. So I need to understand that. It's not that I care or not care where it really is.
Position is a pretty pointless property. What do we actually care about then? Energy and momentum. Conserved properties.
So we care about energy and momentum, conserved properties. Okay.
In fact, Schrodinger's equation is an energy equation. Don't freak out. I'm not going through a full derivation or anything. If you want to see that, you'll find it in excruciating detail in my book. But
Why? Why not derive it in a video?
quantum mechanics is like 90% math. If you want to learn more than just buzzwords, you're going to have to
Why is it so much math? Why can't it be intuitive?
deal with at least a little math. Get on board. Anyway, this is just kinetic energy plus potential energy equals total energy. That's it. That's all this is. A quantum version of the conservation of energy. Half the battle when using this equation is figuring out what the potential energy is. In our case, it's what holds the electrons in the atom, and its influence is entirely radial. You can actually see that pretty clearly in the electron microscope image from earlier. That's why they look like tiny electrons of the conservation of energy. Half the battle when using this equation is figuring out what the potential energy is. In our case, it's what holds the electrons in the atom, and its influence is entirely radial. You can actually see that pretty clearly in the electron microscope.
What?
In our case, it's what holds the electrons in the atom, and its influence is entirely radial. You can actually see that pretty clearly
Oh, it's completely radial.
in the electron microscope image from earlier. That's why they look like tiny spheres, because their influence is radial. To take advantage of this behavior, we'll need one of my favorite tools, spherical coordinates. They're so cool. Oh, shush. Rather than three linear labels like x, y, and z, we use a distance from the center, an angle from the vertical, and an angle around the horizontal. Since the potential energy only depends on the distance from the center, it can be separated in our solution to Schrodinger's equation. It gives us an idea of size, where the angle part gives us an idea of shape. Let's focus on the shapes first. They're called the spherical harmonics. Notice how they're all oriented along the same axis. One angle draws a curve, and then the other angle makes it.
But when we look at gold, when you showed us the scan, then we didn't see these orbitals. We only saw spheres. Can you actually show spheres? Show these these higher harmonics?
To the surface. Each one of these shapes goes with a specific angular momentum. It's what we call orbital angular momentum, because these are orbitals, not orbits. The axis they're lined up with is the direction we're measuring the momentum along. Because this is quantum mechanics, we're only allowed to measure along one axis at a time. It's kind of limited, isn't it? Yeah, but it's actually enough. One number tells us how long this angular momentum arrow is. The other number tells us its orientation by projecting the arrow onto the measurement axis. These two numbers are all you need to know the shape of the orbital. You can even organize them into a nifty chart like this. Man, I love charts. I mean, look at this thing. Yes. Unfortunately, none of those shapes are probability distributions yet, because we left out the radial part. It's only half the solution. Including the radial part turns our shapes into probabilities. It turns these into these, which are further organized by energy level. These are just probability distributions. Brighter spots are where you're more likely to find an electron. Darker spots are where you're less likely to find one. It's a visual of where you might find something, if you looked. We generally don't look, though, because we want the position to be uncertain. That way, the energy and angular momentum remain definite for each state. But like I said at the beginning of the video, this all looks pretty static. Atomic orbitals are actually dynamic. An electron can absorb and release photons, which can change that electron's energy. Electrons can jump between quantum states. Based on what I've mentioned so far, you're probably only imagining a simple fade. But it's actually way cooler than that. Quantum mechanics might be weird, but it's still a set of rules. The events might be probabilistic, but the probabilities are deterministic. And that probability must be conserved, just like energy and momentum. That means you can imagine probability as if it's a fluid filling all of space. When the distribution changes, that probability has to flow to the new locations. Orbital transitions look more like this. That flow is called a probability current. Kind of cool, huh? So what's an atomic orbital? A quantum state of probability. The angular momentum tells us the shape. The energy fills the volume of that shape with detail and gives us an idea of size. Brighter spots are where you're more likely to find an electron. Darker spots are where you're less likely to find one. But the probability of finding the electron somewhere must be 100% at all times. Quantum probability must be conserved. When an electron changes quantum states, that probability has to flow to the new locations in a kind of probability current. So on some level, maybe the cake isn't a lie after all. As long as by cake, you mean probability. So, what do you think? Is the cake a lie? Let us know how you feel in the comments. Thanks for liking and sharing this video. Don't forget to subscribe if you'd like to keep up with us.
That was a very unique way to explain the orbitals. Interesting. Okay, so he says that there is a transition. I don't know why. I mean, you don't need to know the math. If you just show me, at the end of the day, the math can be visualized through these animations. There's nothing special about math. These people, they like worshiping math. It's like they're in a competition. Okay, there's the message. Finally, she wrote a message. Let's see. Oh, so it's not a chick. It's actually something important. Mm-hmm. That's weird. Who is she? Mm-hmm. Mm-hmm. Okay, let me just forward it. Mm-hmm. Mm-hmm. It's good I didn't answer. It's good I didn't pick up the phone. Okay. Mm-hmm. All right, let's continue. So I'm thinking about what he said, if it's helping me. It's good about atomic orbitals. It's interesting information. Still, I mean, it's way too quick. I mean, I have so many questions about everything he showed. It's like, it's the tip of the iceberg. If he can explain, I don't know how he expects anyone. I mean, he's making a video for children, but then he goes into super deep, complex stuff, discusses it very quickly, not in any details. 1 second, let me get the message. Okay, we'll come back to this.
Until next time, remember, it's okay to be a little crazy.
Why does he talk about being crazy? This has nothing to do with being crazy. I mean, he's pretending like the universe is crazy, is weird. Well, what's the point of being crazy? What is this nonsense with the craziness? I don't know. I mean, it's okay to be very crazy. If you want to be crazy, go crazy. You can. Why only a little crazy? You can be as crazy as you want, as long as you're not harming anyone, not harming yourself. I mean, if you want to harm yourself, it's up to you. You can. But how is that relevant to figuring out the universe? You want to figure out the universe. That's one thing. You want to be crazy. That's another thing. I don't even know what it means to be crazy. Like, I don't know what you mean. He has a hot wife. She is hot, so I don't know what he's talking about. They seem to be happy together. Let's continue. Let me just shut down a few. No, yeah, I don't want to watch that. That was useless. That's useless. We need to figure out atomic energy levels. Okay, let's see this guy. But let me first see if I can see the message. One second. One second. Okay, let's watch this.
What is the difference between an electric field and a magnetic field? An electric field is caused by both moving and non-moving electric charges. A magnetic field, on the other hand, is generated by moving charges. The positive charge is the source of the electric field. The negative charge is the sink of the electric field. In nature, negative and positive charges can occur independently of each other as electric monopoles. Magnetic monopoles, on the other hand, as far as we know, do not exist in nature. That means there is no magnetic north pole or magnetic south pole that occurs alone. North pole as a source and
This guy's Scottish or Irish. Feels Scottish.
south pole as a sink always occur together. Magnetic field lines are closed loops. Electric
Let me see the message.
field lines, on the other hand, do not have to be closed, but can, for example, break infinity, like the field lines of a point charge. A charge Q in an electric field E experiences an electric force equal to Q times E. A moving charge in a magnetic field B, perpendicular to the motion, experiences a magnetic force equal to Q times V times B. The unit of the electric field is volt per meter, and the unit of the magnetic field is volt second per spectrum.
Let me see, 1 second.
Meter, or in short, Tesla. When an electric charge is placed in an external electric field, the charge is accelerated. As a result, the charge changes its kinetic energy. On the other hand, when an electric charge is placed in a magnetic field, the charge is not accelerated. The charge does not change its energy. In short, an electric field does work on the charge, but a magnetic field does not. The magnetic field does no work on the charge even when the charge is moving. An electric field can be shielded, for example with the help of a Faraday cage. A magnetic field, on the other hand, cannot be shielded, but at least deflected.
Okay, interesting, but not really. Interesting insights.
Physics for the photoelectric.
Okay, let's watch her.
Look, Albert Einstein was awarded the 1921 Nobel Prize in Physics for the photoelectric effect. But why? At the time, just like now, Einstein was far more famous for his work on relativity. Well, it all has to do with a man named Philip Leonard, whose experiments in the photoelectric effect inspired Einstein's theory. Leonard is a fascinating person who first inspired and befriended Einstein, and then, due to an odd combination of his love of physics, scientific disappointment, nationalism, and mental weakness, became one of Einstein's greatest nemesis. This is a physics story and a story of a man's descent into madness and fascism. So buckle up and let's go.
Okay, I don't know if this is relevant to us. We're past the photoelectric effect. I believe the photoelectric effect. I believe that photons are part like wavelets. like every other particle in the universe. They are sometimes wavelets, other times they're tiny. As wavelets, they are huge. They could be this, like a photon could be the size of of a galaxy if its wavelength is big. So it could. There's no limit to the size of a photon. There's probably maybe there's no. Oh, but is there a limit to the small size of a photon? I don't know. But the big size, there's no limit. It could be the size of the entire universe. Okay, but this is useless for now. Okay, let's watch Zabin's latest video. It's actually very good, very important. Let me see, anything interesting? Actman blames Elon for Brazil's decision. What do you mean Brazil? It's one.
Yesterday to one of my friends who's an indie game developer from Brazil. And he was very upset over the fact that he can't use Twitter anymore. And the reason for it is that since he has an indie game, he worked really hard in order to farm a community on Twitter that will then promote his game. And unfortunately, that's not possible anymore because the politicians in Brazil have to be protected. Like they're very important people, and they cannot be allowed to lose elections. You need to protect their democracy by using non-democratic means, by cracking down on the people's ability to communicate, which is very interesting. Like you need to use fascist tendencies to protect democracy. I think that protecting democracy means freezing the status quo. Like we have reached the level of democracy where it's perfection. Like the correct people have been elected. We have reached perfection. They have the best ideas. They already have a plan for the future of the country, probably for the next 1,000 years, like the 1,000-year life, if you will. And you cannot allow.
So the guy speaking is a lawyer and a doctor from Romania with a really, really hot wife. So, really interesting guy. I followed him since before he started his first bachelor's. So, I mean, he really brilliant guy and really great analysis. I would say some of the time, but sometimes he follows TFM, Turd Flinging Monkey, when it comes to economics and finance. So obviously that's where he has no idea what he's talking about. But when he talks about communism, he has the most incredible insight how exactly the mechanics of communism work, how it always fails. He really explains it from like he was there when it failed. He can explain exactly how it fails. It's really amazing. So okay.
Any interference with the planet. They cannot ever lose elections to populists. Like populists are evil.
Okay, 1 second. Let me get the message. Mm-hmm.
By default, like they represent the popular will of the people. Like you cannot have that. So obviously, sacrifices need to be made. In other cases, businesses and other people like my friend, they should not be allowed to advertise. They should not be allowed to get in touch with other people. And that was just Twitter, but it doesn't mean it can't expand. It doesn't mean that tomorrow it can't be YouTube or it can't be TikTok or Rumble. As we got to see on Reddit, there are already people that are cheering this decision to ban Twitter, and they want more. Like they want other platforms to subject themselves to Brazilian demand. And here's an example with Actman, which has a very interesting take. Farewell to the people of Brazil. We will miss you. Elon has nosedived this site into the fucking gutter. So this is a person using Elon's site, not being banned from Elon's side. Like his business is not going to be affected because as a content creator, you do need Twitter in order to stay up to date with the recent news and also to talk with your subscribers. He's fine, right? But Elon is to blame. It's kind of like blaming the journalists for the Nazis striking them down. Does that make any sense? And not to mention, how is Elon responsible for Brazilian people being fined up to $8,000 for using a VPN? Is that also Elon's fault? I found that very interesting. Again, I was talking with my friend. I was asking him, well, hold on a little bit. Why don't you use a VPN, right? Because this was the take of a lot of people on the internet. It's like, well, the government is incompetent. Like the government just doesn't know what it's doing. You can't just ban a website. I mean, obviously people are going to use VPNs, and the answer is yes, you can, and then you can get an $8,000 fine then. Are you going to risk it? I mean, chances are you may get away. If you're a small content creator, if you're not making a big footprint, like maybe. But can you sleep at night knowing that if the government catches you, it's $8,000 per day, and you've been using it for a month? Right? Like, is that something? And my God, the position of the government, absolutely adorable. Like, imagine that you have 10 people that are using your house. You're renting it to 10 people. You got a big house like a Sandpike. But you also say that now you need to provide safety for the people in that house. And every single time someone says something you don't like, $8,000 fine. Isn't that a nice position to be in? Like, you're generating wealth. I used to say that governments can't generate wealth. I was sorry. I was wrong. Yeah, they can have laws like this, where if you flap your mouth and make certain vocal cords, or if you do the clap on the keyboard, $8,000 fine. Plus, please. Now,
Okay, 1 second. I need to look at a message. 1 second. One second. Okay, one more message. Okay.
Dangerous misinformation that leftists are espousing is that Twitter had to be shut down because of misinformation. So for some reason, human beings do not have the right to be misinformed anymore. Like if I, as an adult, want to be misinformed, and this is what I demand. I want to be misinformed. I demand someone misinforms me. Apparently, I don't have that right anymore. The only people that do have the right now to use Twitter, and this is what I told my fellow developer, like, look, if you want to use Twitter and you can't use a VPN, there is a legal way to do it. You just gotta get into your leftist party and reach the top, because it seems that politicians from the left in Brazil are still tweeting. So like, this is what you gotta do. You just gotta go to the top, and you need to become a decent leftist, aka you reach the mythical status of
Oh, so the politicians are still tweeting. That's interesting. How's that possible?
decent human being, and then you can tweet as well. But was it misinformation though? Was it really misinformation that got Twitter banned? Well, no. Apparently, Elon Musk has said that he was asked to do something which is against the Brazilian law. Because like if you look at Elon Musk,
So he was asked to do something against the Brazilian law. Well, let's check the audio. So he was asked to do something against the Brazilian law. Amazing. Okay.
his behavior, he has complied with other nation states' requests, even when they went against free speech. And he would say, well, yeah, but we have to do it because that's their law, and we still want to have Twitter in their company, so I have to consider whether or not it's worth doing. Right? So like, he has complied when other countries asked him to do stuff. However, in the case of Brazil, he didn't, and he justifies that what he was asked to do went against the Brazilian law. And it's funny because a lot of Twitter users and leftists go, well, why did that happen? Why is that? I mean, literally, this is something that you would show to a 5-year-old to understand. Like, if you're watching this and your brain cannot comprehend, then I don't want to have a conversation with you because you do not understand reality. Like, to me, it's baffling that you understand like all these complex issues like gender studies and other academic concepts, but you can't seem to grasp this. So look at this. Again, this is what Elon Musk is claiming, right? So like, if he is wrong, he can be sued on this. But like, no one is doubting what he's saying is true. Like, no one is saying, no, actually, we never asked for this. Elon is lying. He's saying that the order from Alexandre de Moraes came. X must block within 2 hours and in secret the following accounts, including that of a sitting Brazilian senator in their entirety, without any reference to a single illegal post from any of the accounts. So you guys know how social media sometimes just bans someone without mentioning what they did? Like they never say, oh, this is the post that has you in violation. They will just shut down your channel and say, this channel has been shut down for violation of TOS. Do you know that? Like, this is probably why it's happening. Like, you may have government entities, in this case it's Brazil, but I wouldn't be surprised if similar requests comes from UK or Germany or other places, where they basically say, yeah, and these are the people we need you to ban. And not tell entities and not show any posts, just ban them. And I do think that would comply. If it was Facebook, they'd be like, yeah, sure, yeah, we're banning them. Meanwhile, according to the Federal Constitution of Brazil, all persons are equal before the law without any distinction whatsoever. Brazilian foreigners residing in the country being ensured of inviolability of the right to life, liberty, equality, the security, and property of the following terms. The expression of thought is free, and anonymity is forbidden. The expression of intellectual, artistic, scientific, and communication activity is free, independently of censorship or license. Any and all censorship of a political, ideological, and artistic nature is forbidden.
Wow.
Paragraph 1 of Article 19, the court order concerning illegal content shall contain, on pain of voidability, right? So like the Constitution says that if you do this, it's no, you don't have to follow it, a clear and specific identification of the purportedly infringing content. So in other words, this request, without any reference to a single illegal post from any of the accounts, is in violation of the law. Now, of course, maybe Elon Musk is lying. Maybe this wasn't true. Maybe this wasn't requested. But I haven't seen Brazil denying it. I haven't seen any official from Brazil saying, no, actually, we would never request something like this. So what's interesting with this Alexandre de Moraes, because I was looking at it and I was like, well, hold on a little bit. Why does he have so much power? Like, isn't this something that politicians should do? Like, shouldn't politicians draft a bill which would ban X? Like in America, for instance, with the TikTok ban. Like, you have politicians actually doing it. Like, why is the judge doing it? And it turns out that he's not just like a random judge. He has so much power that Elon Musk is now calling him a dictator. And it's not really far from the truth because he has legislative powers, he has judicial powers, he does hold a lot of power. It's not like the VPN thing. A lot of Brazilians are saying that it's a law that came overnight. And I tend to believe it because I have seen Brazilians using VPNs up until now, which shows that it wasn't illegal. And a lot of people use VPNs not for anonymity, but for protection. Like, it protects you against certain types of malware and against certain types of scams. So people have used it, but yeah, if you're in Brazil, and make sure you disable it. It's $8,000, right? Please. Yeah, so a lot of leftists are omitting this from the conversation. Like, this just doesn't register. They're like creationists. You know, like creationists who thought that the earth is 6,000 years old, and you would bring arguments, and they'll just dismiss it. They'll just ignore it. They would pretend that they've never heard the conversation, ever. I find this to be absolutely fascinating. So yeah, this is why I agree with Elon Musk. Because on one hand, they're confident their rules. I get that. Like if you're having a nation that's more fascistic oriented and you want to build a 1,000-year-old empire, like, you got your own laws, you got your own rules. But the problem is, like, when your own laws are violating the constitution, you're not but more importantly, is this thing where you want to do it in secret, right? So like Elon Musk now should have taken the blame for banning people in another country, so that it doesn't look like, well, actually the judge wants them to be banned. No, it's Elon Musk banning them for violating Twitter's TOS. It's like, why should he take this responsibility? Why should he take this burden? Like, if you want to ban and censor, fine, but you need to take responsibility for the banning and censoring. Which is also interesting. Why do these governments not want to stand behind their censorship? Why do they have to constantly laugh at it? This is what I don't understand. Just own up to it. Fucking own up to it. The Brits own up to it. I mean, when they wanted the X to ban, I think it was Tommy Robinson, right? There were members from Labour and they signed their name on the petition and they were like, here, we want it banned. Boom.
Okay, interesting. Start over. La 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 la. This guy has a hot Russian wife. Physicist that validated the existence of atoms. Let me get this message 1 second. What is this? Okay. What else is new? Permittivity and displacement. Interesting.
Hi, welcome to the next in our series of Practical Electromagnetic for Engineers. It turns out that the electric field depends somewhat on the material you're working with. The electric field in vacuum and the electric material and plastic material, for example, may be different. There's some subtle distinctions between the two that we're going to explore in today's lecture. But the only materials we're going to be talking about are insulators.
So this is
called dielectrics. So we've spent a fair amount of time considering a chart.
So this is interesting. This is for engineers. Interesting. Because engineers can't afford to talk about nonsense, unlike theoretical physicists who can afford to, who get paid to talk about nonsense, to contemplate anything and everything, and get lost in their own, get completely lost. And in some respect, it's fine. But engineers are much more practical. They have to be. 1 second, let me see a message. 1 second. Okay, let's see. Let's start over.
Hi, welcome to the next in our series of
Practical Electromagnetics for Engineer. The electric field in dielectric materials. I don't know what dielectric means.
Electromagnetic for Engineers. It turns out that the electric field depends somewhat on the material you're working with. The electric field in vacuum and the electric material and the plastic material, for example, may be different. There's some subtle distinctions between the two that we're going to explore in today's lecture. But the only materials we're going to be talking about are insulators, a type of material we call dielectrics. So we've
dielectric is an insulator, like plastic. Okay. This is interesting. So this is the electric field in material. So there is an electric source. Let me get the message. Let me create a group. Is there a group with this guy? Let me check. Can I see what groups I have with him? Oh, only one group. Okay, 1 second. So let's create a group out of this guy. You can't on the laptop? Okay. So create new group. So we are going to have, I need to remove some keyboards. one person to, what's his name? There it is. Mm-hmm. 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 One second. Okay. So we need to find it. Mm-hmm. So these two. So forward, forward, no. Forward, 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 this. Mm-hmm. All right. So this is very interesting, really interesting. So we have an electric source here, and the electric field, the vector field, is a function of the radius. I don't know what m is. So the radius is a vector, is q over 4 pi epsilon, where epsilon is a constant. It should be epsilon naught. So it's a constant of the material times r minus r. Why do you need, but rq is probably 0. So the r of the test particle probably. So it's 1 over, it should be the distance squared. But the distance squared, we lose the vector, and we need to know what the vector is. So this is the vector. That's fine. Okay.
Spent a fair amount of time considering a charge. Let's call this a charge Q down here in free space. And we know that it creates an electric field, which is given by a vector field we call E. Essentially, at every point in space, we measure it, which is determined by a vector R sub m. So, of course, R comes in. R sub
Okay, so this is the R of the measurement. Okay.
m comes out here to some point we want to measure. We know when we get the expression from Coulomb's law that the electric field depends on this term epsilon. We said was a proportionality constant. Essentially, it relates the actual electric field in some kind of MKS unit system to
Why do you call it a proportionality? This is the permittivity or something. It's how much the ether permits the propagation of this field.
do things and balance things out. The question is, why don't we just put in a number? What if R sub m is inside some block of material? It turns out that the properties of this material are generally represented by epsilon. That's why we have a variable epsilon here rather than just some number. Because if we use a different material, we have to change the value of this proportionality constant. So why does this happen? And what implications does it have for working with electromagnetic stuff? In order to better understand this, we need to zoom in. We need to sort of get a microscope and zoom in very closely to look down on the scale of the individual atoms or molecules that make up this material. So let's go ahead and do that.
That's very interesting. So the material itself, but we know that even in a vacuum, you have this epsilon. One second, I have an email. Let's check the email. 1 second, what's going on? Okay. Okay, that's good. Okay, we'll come back to this. It's fine. We'll come back to it. Okay, let me check the message. That's good. Okay.
Do that. So if we zoom in far enough to this material and take a somewhat simplistic view, and then the reality is, of course, much more complicated, we know this material is made up of individual atoms or molecules. And at the center of each...
One second, my phone. What's the battery status on my phone? 20%. Potent! It's 20%. And this one is 70%. It's good. I am hungry. I should go grab a bite. This is interesting stuff. Okay. It's good stuff. We didn't do any research, so let's modify this, the name of the title. So we just did research. So research. What did we research? Magnetic and electric quantum effects. Something like that. It's research. Okay. So let's stop here. I'll go grab a bite and I'll be back. Bye for now.